Now, without further ado, I'm sure you'll enjoy it, and I'm sure you will do an amazing job today. And Angeliki, Elena, the stage is yours, and good luck.
Okay, so yeah, hi everyone, and we are very excited to be doing that tutorial. We'll be talking. So I'm Angeliki, and Elena, and Elena is here. Yeah, she will be giving the. Hi, Elena. Elena will be giving the second part of the talk. So we are going to be talking about language modeling, transformers, and beyond. We will aim to have like a small break in the middle to allow people to get some water, etc. But we'll adjust the timing, depending on like how we are progressing. Okay, so I'll start by talking a bit about language modeling, breezing through, a bit of the history of language modeling just to set up the scene, and then we'll just, deep dive, head first into the transformer language model, which is perhaps like the most widely used language model today. And then Elena will take over to talk about some exciting applications of transformers out there. You can see the slides moving, right?
Yes, everything is fine.
Okay, great. Okay. So first things first, what is language modeling? So I am going to show that with an example. This usually goes a bit better when not in a virtual presentation, but in an actual presentation, but like we'll see what we can do. So here is a sentence. She was close behind it when she turned the corner, but the, can you guess the word that follows? Anyway, I'll assume that people cannot guess the word. It's actually a pretty hard one. But note that this is exactly basically what language models are faced to do. Like they get a bit of context and they need to predict the next word. Now, this is like a particularly difficult one. We don't know who is she, what is it, where is this happening. It's a pretty hard task so far. Now, let's try to make your life a bit easier. So I'm going to unveil a bit more context here. I'm not going to read it, but basically we see that, Alice comes into play and there is something that has ears and whiskers. So can you now guess what the is? Well, it becomes a bit easier. I mean, I'll tell you that. Now, if I actually go on and reveal a bit more context, you'll see that there is, the more context I reveal, the more information you get. For example, we know we see things in the context like white rabbit, and then using all these clues together, it becomes easier for us to predict that the missing word was actually rabbit. And this is a next from Alice in Wonderland. So this task that you had to do, and it was actually even difficult for you, especially with the lack of context. Imagine, how difficult it is for our models to do. So what language modeling is basically using the answers that using the answers in the missing context to estimate the probability over the continuation of that passage. And the single most important property of language modeling is that all these continuations should basically sum to one, and that's about it. So, for example, in this particular example that I showed, rabbit is the most plausible continuation, with dog and cat, also being somewhat plausible. But as you also saw, depending on what slide I was using to show you, these probabilities were actually, somewhat different. So in the first slide where you didn't have a lot of context, it wasn't clear which of these words was actually the right continuation. So I hope I made the point that modeling word probability is actually really hard, even for humans, many humans. But we shouldn't give up hope because, and the main reason for that being that the basic property that models have is very powerful. So the basic property that language modeling has is that it's able to give us higher probability for better utterances than worse ones. And we can think of better utterances, for example, as being grammatical utterances, fitting some context, etc. But this property, though, empowers a number of tasks that we want to do in natural language and in general sequence modeling. Because if you think about it, we can model a multitude of tasks as just being, some sequence prediction, some next word prediction. So for example, we can think of machine translation as being sequence predictions from the in this case, from Greek to English, or question answering from, predicting the continuation from the question to an answer, etc., etc. And virtually, basically, any sequence tasks could be treated in the language modeling sense. So the question then arises, how can we actually model this P of X? And just a reminder here that if we had a way to estimate P of X, then this will allow us to sample, that is, to generate sequences, but also to score them. I forgot to say that if you have questions, it's better to post them as they come so that, we can clarify them and then continue. So yeah, please feel free to ask if you have any sort of questions. Okay, so how do we model P of X? Now, the simplest thing that we could do is to start by modeling P of X as just being, a bigram model. Now, sorry, not a bigram, a unigram model. So what this means is that to estimate P of X, we count the unigram probability, the unigram probabilities of words. So we go out there and we count words, basically. And while this is very easy, the problem is that because of that independence, if we would use this P of X to generate a sentence, we would end up generating something like the, just because the unigram probability of so how many times the appears in a corpus is like vastly higher than anything else out there. So while this is easy, it's on its own like a pretty useless language model. Now, a more realistic language model is the one that actually assumes some conditional dependence of words. And this is a fancy way to say that it's a model that actually takes into account the context. So in this way, for example, what this means is that we estimate the probability of words by taking into consideration the words that have appeared just before that target word. Now, this already starts becoming, more complex because it's not just about counting single words, but we have now a joint probability in our hands that we need to estimate it from conditional probabilities. For example, from conditional probabilities. And the way that we are able to do that is because we can very nicely decompose, we can do divide and conquer. We can use chain rule to decompose modeling P of X as a way of modeling, the individual constituents. So we start, for example, by modeling the first word, and then the first given the second word, and then the third word given the first and the second, and so on and so forth. So while this is great. I mean, now we have a tool that we can estimate conditional probabilities. And if we wanted, for example, to estimate bigram probabilities, we could do something like this. How many times, modeling exists after modeling. Sorry, before modeling exists before word, and so on and so forth. And we could count things and we can have these probabilities. So this is easy. The problem is that we can't just do this only for 2 words or for 4 words, because we don't just have 4 words. We have like a number of words out there. And actually the number of words is not even a closed class word, it's open class. Like we constantly have new words coming up. So we are faced with like a very difficult problem, and out of like scaling up the counting to many things and like even more things, because all these counts basically grow exponentially the more context we want to account for. So we are faced with a very hard problem, basically, because of us wanting to have like an expressive model. So the NLP, it's fair to say that the one of the main bits of NLP is actually find a way to effectively and without loss of expressivity give us a way to do this sequence modeling. So one of the, as I showed before, one of the first ways that people try to do language modeling is this count-based n-gram way, and this goes back actually, to Shannon in the like early 50s. So it's like a very basic idea originating from way back, and it's very intuitive. And what this basically means is that we don't have like infinite context anymore, because this is not scalable. We are going to assume like some sort of like fixed context. So we are going to model, for example, trigrams, as in this case. So you see, we are not now modeling the whole infinite context, but we are cutting everything down into trigrams. And this actually pretty neat idea, because we can do like quite a lot of things with trigrams. However, I mean, as you can imagine, with trigrams, we don't have infinite context. Like we have like a limited temporal range, which is we can only model words with a context up to 2. And this is like pretty, like it's pretty limited. Like we can't have like a rich understanding, a good handle of words if we just consider, the previous 2 words. However, even if we could live with that, the major problem at the end of the day with these count-based n-grams is the fact that if you haven't seen an n-gram combination, you can't assign a probability to it. And as I said before, the language is like, it's like an ever-evolving communication medium. So we constantly have, new words coming up. And n-gram language models, it's very, very, very limiting with that respect. I don't know if you know, like, probably you can recognize this guy, but Alan Turing, already from back then, has proposed ways, for example, that we can do this smoothing, so that even if you haven't seen an n-gram, we can at least have a way to estimate a probability for it. For example, by falling back to the count of the bigram, and the unigram. Despite all this, like sort of like challenging things with n-grams, people really loved n-grams, and they tried to boost a lot. So for example, even in 2007, we Google was like a company like Google was really basing a lot of research on n-grams, and also how to scale n-grams into like a trillion tokens. So thinking about how to improve things, probably you've already heard into previous tutorials already, but using word vectors, things like word2vec, is a neat way that can allow us to do fuzzy matching between words. So the idea then that followed here was to be able to not just operate on words as strings, as discrete items, but rather operate with words using their vectorial representation. And so what this means is that all the models that have followed after n-grams, they take as input word representations, and then they learn some function f that is going to predict the next word. A lot of research went into what is this, mysterious function f. And when people design these functions, they have in mind some desirable properties, like, the order should matter, in the same way that orders matters in language. I can't just start talking now in bag of words way. You'll probably not, you wouldn't be able to follow what I'm saying. It needs to have a variable length, because sometimes we can have small context, a lot, or like a big context. It needs to be learnable, that is, it needs to be differentiable, so that we can have a loss function, then we can optimize the weights. And it needs to be able so that the individual changes to that function can have large effects into the input. So it needs to be basically, the notion of deepness and nonlinearity here. As I will mention throughout the talk, and you'll probably, you are aware of this already, but unfortunately there is no freelance out there. So, we will gain something, but we will also lose something over the years. Even with transformers, transformers, they don't really capture all these things still today. So building on this vectorization, the next plausible step, not in time but conceptually, was to basically do what n-grams were doing, but now with vectors. So just with vectors, which is great, and it gives us this representational smoothing. However, it's still memoryless, right? And it still has limited temporal range. So we can only model, 5 grams or trigrams or whatever we started the model with. A big change to n-grams was actually, before the neural n-grams, was recurrent neural networks, RNNs. And RNNs promised us infinite memory, because we are now basically modeling the sequence as it comes, and we incorporating any new word into this function f. And it promised us also, like infinite n-grams. So in theory, this sounded like an excellent model, like a magic model. However, in practice, the training of this magic model turned out to be quite difficult, especially, the longer the context became. The reason why the reason why it was difficult to train was because if you think of an RNN, you can unroll the RNN, and RNN is essentially like a very, 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 very deep neural network. So I want to give you just an intuition of why it's very difficult to use backpropagation, which is the standard learning algorithm to train neural networks. But you can think, and also just a short video, but the idea is that the longer the sequence is that you need to be able to propagate a signal, the more difficult it becomes for that signal to be basically propagated without noise. And this is just a simple video that shows, something similar, that the more basically you need to relay information from one person to another, the more this information gets diluted, noise gets inserted, and at the end of the chain, what the first guys draw is completely different from what the first person drew. And here people just try to understand from the movement in the back what was the original image. So practically, what this means is that with RNNs, we had the problem of basically vanishing and exploding gradient. So in practice, we weren't really able to get all this temporal range that we were promised. Of course, people worked in solutions. So people worked in, having some sort of solutions, and even something simple as, clipping the gradient, which is just basically limiting the size of the update, was able to stabilize some of the training of these models. However, the biggest in this class of models, the biggest, let's say, win came with somewhat alternative modeling architectures, like still recurrent, like things like LSTM or GRUs that are better suited to navigate, let's say, the learning dynamics of the model. So LSTMs made us possible to train, for example, larger models than what RNNs would allow us to do. Over the years, there have been a number of variants of LSTMs, like any sort of variant that you can think of. Somebody had implemented it. However, and I guess this is like something to have in mind, is that still a properly trained and regularized LSTM was very difficult to beat. And I guess there is like an interesting overall takeaway here is that, when you work with baselines, give some love basically to your baselines, so that all the comparisons that you get, you can trust. Yeah, that's basically. The next big, let's say, revolution in language modeling came with the transformers paper, and with the self-attention is all you need paper. I'm going to deep dive a bit later into self-attention, but self-attention is basically nothing more than contextualizing the representations that models have within a layer. However, ordinary transformers are actually n-grams in disguise because they have like a limited limited context that they receive. So if you remember the freelance that I said before, this is sort of what we have to pay for the expressivity that the transformers have. We can do great things with transformers, but we can only model a particular context length. So not infinite as with RNNs. But this is, this is still okay, and we can do amazing things with transformers. Now, the self-attention has empowered a number of like great models out there. BERT, I mean, I'm sure you've all heard about BERT. BERT is one of those models. BERT is an encoder model that creates representations for a given input. And the biggest, let's say, the biggest to be able to get a model like BERT, two things happened on top of self-attention. Byte pair encoding, so BPE, that is not modeling anymore words as words, but modeling words based on subword units, which again allows us, to model whole words even if we haven't seen them before as a whole. And also masked language modeling as a training loss. And if you heard already about word2vec, this kind of, seems like the skip-gram objective of word2vec. The next, let's say, achievement was GPT-2. So unlike BERT, which is the encoder that creates representation, GPT-2 is a decoder. So given words, predicts the next word. So you can use it to decode from the model. And on top of the transformer, basically, GPT-2 did three things on top of the original transformer. The major thing was it actually scaled the number of parameters. It also used BPE to be able to represent words based on subwords, but it also used a large amount of web text to train such a model. Finally, this brings us to GPT-3, which is a bit like GPT-2, but everything is now bigger. So GPT-3 has more scale, and GPT-3 was trained in even more text than GPT-2, plus other stuff. I'm not going to refer a lot to GPT-3, but Elena will give like a very nice overview of what GPT-3 is and the key elements that make GPT-3 such an ubiquitous model. Now, I want to take now a few minutes to talk about transformers, because this is basically the model of choice in most of the NLP models and techniques that we see today. The main idea with transformers is, I guess, based on like these three key ingredients. First of all, transformers incorporate information, what we call positional embeddings, to the input representations of words, to the input word embeddings. And the main reason for that is that so that order can matter. And if you remember from the beginning of the talk, modeling the order of words is one of these desirable properties that we would want to have from this F function. The next main idea that transformers brought is attention, which is, as we mentioned before, is to contextualize the input that we get. We don't actually have one attention, but transformers have multi-head attention, so that to allow us to contextualize the input in different ways. Finally, because this is deep learning, we had a lot of stacked blocks. The main reason being, that deeper models tend to be more powerful. So now I'm going to unpack a bit this notion so that we can get a bit better understanding of what transformer is and why it works so well. The original transformer paper was actually stacked blocks of an encoder and decoder. What this means is that it took as input a sequence, passed it through the encoder-decoder blocks, and then produced an output sequence. To unpack it a bit more, the encoder-decoder blocks are nothing else than the same operation, for example, encoder operation, repeated multiple times. So the same operation in a for loop. However, note that there is no weight sharing here across the layers, and each layer has its own set of weights, which allows transformer basically to have a very big expressivity. And the same holds for the decoder as well. Now, looking a bit deeper into how the encoder and the decoder look like, we can see that the main ingredients for both of these blocks are actually fairly similar. So the decoder has a self-attention layer and a feed-forward layer, its decoder. And the very same thing is for the decoder, self-attention and feed-forward, with an addition of like an encoder-decoder attention, so that the decoder can also attend to the encoder. Again, despite the similarities, there is no weight sharing. Encoder and decoder have their own weights for expressivity. Now, taking a closer look on the encoder, we see that an encoder takes as input a set of words and returns, so a set of vectors essentially, and it returns as many vectors as it took as input. So if we take as input 3 vectors, we are going to return 3 vectors. Note that this already starts being a bit different from the type of deep learning architecture that we are used to, because usually, for example, if we think about how ConvNets work, we were used to this almost pyramid sort of shape, where we start with wide networks, and as we go to the top, the networks used to become smaller and smaller, so that's to have basically increased abstraction. The code transformer doesn't have this, so it's constantly, the same operation. So it's like this rather than that. I mean, just to put it visually. Now, the self-attention. Conceptually, the self-attention, it's a very intuitive, it's like a very simple operation. And the process that the self-attention follows is actually very, very, very similar to the contextualization in word embeddings. So, for example, think of the differences between Word2Vec and Elmo embeddings. Elmo embeddings is the contextualized version of Word2Vec. Now, the reason why contextualization is so important is because it allows us to extract more information from a single word. So in this particular example that I'm showing here, let's say that for the word eat, we want to derive a representation within the model. Without self-attention, it wouldn't be easy to understand, to have like a good representation of it, because it as a word has like a very, it doesn't really mean anything out of context. The moment, though, that we consider it within the context of other words, we can already start building a better representation of it. Because in this particular context, it essentially relates to the animal, which also exists in this particular sentence. So self-attention, it basically allows us to extract more for the meaning of words by leveraging the context that each word exists. Simple but powerful idea overall. Now, let's try to see what exactly that notion of how that notion of contextualization is operationalized in the network. So the self-attention is going to take one word, for example, eat, and is going to give us out another word for it, but now that being the contextualized version of it. In practice, what this means is that it, the new version of it, Z1 in this case, in the picture, is going to be the weighted average of all the vectors in the context. So it now is going to be some weighted average of all the other vectors in that particular sentence that it existed. So there are two questions here that we would have to answer. How to estimate that weight so that we can do the weighted average, but also what exactly we are summing. So what are the vectors that we are going to sum to produce it? So let's see now what we need to do for each word. So we are now going to talk here for the word it, so for Z1. But the same process is going to be applied to all the other words. So for it, for Z1, we will need to learn 3 vectors: the query, the key, and the value. We will use the query vector for the word it, and then we will calculate the dot product with all key vectors of all the other words, including itself. So we will take it, we'll take the query vector, and then do dot product using the key vectors of all the other words in the sentence. Now, having this dot product across all the words in the sentence, we will normalize this using softmax. And notice that this normalization is basically what is referred to as attention. because so this normalized version is what, for example, in the original paper of attention by Dmitry Badanov was referred to. Now, having these weights, now we are going to use the weight for it. We are going basically to have one weight score per context word, such that now all the weights sum to 1. And then we will take this weight for every context word, and we will use the value so we will use the weights and the values to derive the new representation as the weighted sum. Now, something that is interesting to notice here is that this process is for one word, but the same process happens for all the words in the sentence. But as you can see already, this for loop here is independent for one word to another. So we can do this thing in parallel. And this is why this is one of the reasons why we say that transformers can be parallelizable, and why we can scale them up, because it allows us to train them basically faster and more scalable, because we can do this operation in parallel. Now, this was so this is one way to do self-attention, or this was a particular self-attention similarity. However, intuitively, there are many different ways that we can compare words with each other. For example, we can talk about semantic similarity of words, or syntactic similarity, or topic similarity, or common suffix similarity, or words with even number of words with even number of letters similarity, etc., etc. So when we can have many similarities, why just constrain ourselves to one? What this practically means is that the same operation is repeated in different ways in the network. So we don't just derive for every word one query vector or one set of query key value vector, but we derive a number of those. And at the end of the day, instead of just having a single output, we have one output vector for each of these, what we call attention heads, which we then concatenate all together, and we feed to a linear transformation so that we get a single vector out. Because as we said, one vector in, one vector out. The final step is that we take the representation that the multi-head attention has created, so this vector, and then we pass it through a feed-forward network. And again, one vector in, one vector out. An interesting question to ask is, what are actually layers learning in Transformer? We talked before about the notion of how older networks used to have this pyramid version, starting from like wide networks, and then us going up, learning more abstract representations. Interestingly, Transformer has the exact same property without having this explicit triangular format. So we see here that layers that are closer to the input capture more shallow patterns. So things like, common n-grams. And these patterns become more and more semantic the closer we get to the output layer. We can see here, for example, that layer 1 has more, the blue, which has more shallow, but blue gets smaller as we go to layer 16, and green, which is the semantic, tends to overtake here. Now, what do I mean by semantic and shallow? We can see here that in early shallow patterns is things, for example, that things that end with substitute. So we can have particular bits in the network that get highly activated when a sentence ends with substitute. With more semantic, we mean that sentences, for example, talk about things that have to do with TV shows, as in the very last example. And then the network basically learns all of these patterns that get combined together to do the final task. So now, putting it all together, I hope that it might be easier now to see this picture, which for me seems a bit scary in the beginning, but like going through the tutorial, actually, I feel more comfortable looking at the picture and actually getting a bit of an idea of what's going on. A couple of things that I didn't refer to, but I think would be interesting to talk about is, as I said, the positional encoding that gives us a way to represent order is nothing else than basically learning a particular vector for every position and then adding that that vector to the input vector of the word as a way to get an input vector with some time information. The second bit that I would like to mention is the fact that the transformer has a number of other tricks added to it. Things like, for example, a skip connection. A skip connection is basically something that takes the input to a block and pipes it all the way into the output of the block. And things like layer normalization. Now, all these things, all these tricks are not particular to transformer. These are actually classic tricks originated from training deep networks. Because at the end of the day, transformer is a very deep network. To put this in context, GPT-3 has 96 blocks, so 96 repetitions, vertical. And within a block, there are 96 attention heads, so horizontal. And we need to have basically good ways to train these models. But because of the way transformer has been laid out, and because of some of the reasons that I mentioned before, despite the fact that we can scale it so much in size, the architecture of transformer and how we can parallelize things make it easier for us to train them at scale. So that was the first part, and I hope, I hope I gave a bit of insights into how transformer works. I'm not sure if there are any questions at this point that people would want to ask.
I didn't write in chat, so if there are questions, write it down now, please. In this time, I just want to thank you for your presentation. It was very interesting. I heard about this information before, but now it's more clear. And I hope it's more clear for the attendees too.
Great. Okay, then if there are no questions, maybe we can have a short, very short break for people to, I don't know, to go get a glass of water or something.
Hi, everyone. I'm Elena. I will speak about all the amazing models that were built in the last 3 years using transformer architecture. If you have any questions, please do not hesitate to interrupt me anytime or post them in the channel. To start with, on the light note, here's the example of a transformer poetry. GPT-3 model prompted with a passage from Shakespeare's sonnet continues generating in style. So you can see that it captures the rhythm of poetry and style. Sometimes some passages sound quite funny, but overall it's an impressive jump in model performance. What are the key points about GPT-3? So the GPT-3 model has been released by OpenAI in 2020, and it immediately attracted a lot of attention of researchers and also everyone actually, because of its impressive text generation abilities and abilities to generalize to a wide variety of tasks from just a couple of examples. So the key points about GPT-3, one relates to transformer architecture. So as Angeliki explained, transformers can be much better parallelized than previous architectures like RNN or LSTM. And this allows to scale them up in terms of number of parameters. So GPT-3 model contains 175 billion parameters. To train such big model, OpenAI also compiled a very large data set, which contains both uncurated and curated data. So data set is diverse and less clean, but this diversity gives rise to powerful meta-learning skills. So what was the state of NLP before GPT-3? So the improvements in neural architecture led to development of task-agnostic models like transformer. However, while the architecture was task-agnostic, we still need large-scale data sets for fine-tuning to specific tasks. So, for instance, if we want to teach model to do question answering, we probably would need about 100,000 labeled examples to properly demonstrate this. At the same time, as humans, we know that we can understand what is required just from a couple of explanations. So GPT-3 model, to build GPT-3 model, the researchers recognized that further scaling up model to 175 billion parameters would improve performance, because it's been already observed in the previous years that size correlated to performance. GPT-3 made a huge leap in performance of in-context learning. So in-context learning, meaning I will explain on the next slides, but at the high level, in-context learning substantially reduces need for large task-specific data sets. And GPT-3 also, as you've seen on the previous slide, and you can find many examples on the internet, it also has impressive abilities for text generation, very fluent human-like text. So from what data GPT-3 was trained? One part of it, one part of the training data set is the common crawl. And this is uncurated data set, basically. It's of lower quality because it contains a lot of duplicates. So it was filtered to remove as many duplicates as possible, but it was recognized that the quality was still lower than that of curated data sets. To mitigate this, at least partly, other high quality data sets like Wikipedia, books were added into the mix. And this you can see that the weight of different data sets in the training mix. Important thing to note is that GPT-3 used only 300 billion tokens for training, so it didn't use. So GPT-3 didn't go over all data, when choosing samples for training, a higher quality data set, as Wikipedia, for instance, were oversampled in comparison to common crawl. So, for instance, during training, GPT-3 saw Wikipedia 3 epochs of Wikipedia versus just 0.4 epochs of common crawl. Scaling law. So why does scale really correlate to better performance? So on this chart, we see validation loss of language models of different sizes, also as a function of compute spend. So you see that the language modeling performance follows power law with respect to the number of parameters, given sufficient amount of compute. Importantly, GPT-3 demonstrates that improvements in cross-entropy loss are correlated to performance gains across a broad spectrum of natural language tasks. So they train model with cross-entropy loss, but then evaluate on a variety of downstream tasks. In-context learning that I mentioned previously. So what is in-context learning? Because the data set used for training is very diverse, it contains various examples that include basic arithmetics. Also, there might be typos, but the typos that observed in different contexts would allow model to understand that, for instance, breed in the appropriate context should be a bird, or what are the examples here? So basically, the model learns to recognize typos and correct them. So few-shot prompting. This is something very important. So as I mentioned in the beginning, before GPT-3, the main driver for improving model performance on downstream tasks were collecting large supervised data sets and fine-tuning models into this data set. However, this oftentimes, so it's impractical. It can be impractical because collecting large data sets for all tasks is expensive and not always possible. But it also, this fine-tuning oftentimes might lead to overfitting. And general motivation is to use few-shot prompting of a generalist model, the model that hasn't been fine-tuned to any specific task. So what is few-shot prompting? Few-shot prompting is similar to how you would explain a task to another human or to a child by using a set of examples. So for instance, zero-shot prompting, we can ask the model, we can give a text-based instruction to the model, translate English to French, and then ask to translate word cheese. And in few-shot prompting, we first demonstrate what does it mean to translate by providing a couple of examples and then prompting the model to translate cheese. So this is different to fine-tuning because essentially no updates of the model parameters happen here. The few-shot examples are presented to the model through the prompt. Another interesting observation from GPT-3 is that scaling the model improves end-shot performance. So the chart here shows how the accuracy model on average accuracy model averaged across all the downstream tasks scale with a number of parameters. From 100 million model all the way to 175 billion, so the GPT-3 size. And different lines correspond to zero-shot, one-shot, and few-shot. So zero-shot, just no examples, and few-shot, several examples. And we can see that the scaling model to 175 billion parameters substantially improved performance, especially for the few-shot. As much as we would love the model to understand all tasks just from a few examples, it seems that the scaling models does not equally improve all types of tasks. So for instance, on the left-hand side, you can see chart of how scaling affects performance on Trivia QA. So Trivia QA as a data set collected from Trivia game. By the time we reach the size of GPT-3, the model performs, from few shot, model performs in line with state-of-the-art fine-tuned model. However, on the right-hand side, you can see chart which shows results for the basic arithmetic tasks. And here, interestingly, for instance, the arithmetic tasks that require single-digit operations, but with 3 components, performance barely improves with size. So basically, and we see many other examples like tasks that require common sense reasoning or complex reasoning. So basically, on one hand, we can talk about whether the task is well represented in the pre-training data, and also whether just unsupervised way of learning from data is sufficient for some of the tasks. Because we want to rely on these demonstrations provided through the prompt, the way how to construct the prompt becomes important. So just again to remind, so the prompt is a set of formatted examples that we pass into the model context. What to put in the prompt and how to structure it can drastically affect performance. So for instance, on the question answering tasks, something that also we observed in our own experiments, depending on if you put in few short examples, if you put context, question, answer, or question, context, answer, or context, question, answer. So basically swapping order of context and question can lead to performance differences of up to 20%. And then this nice paper shown here basically provides a systematic survey of various approaches to learn to better prompt language models. I think there are basically two views on this problem of the problem of sensitivity of the results to the prompt. Some people consider this as a feature, something that we need to leverage and learn to do better, either through reinforcement learning or through some sort of systematic classification of examples. And then there's another view on this, saying that it's potentially a bug and just sort of manifestation of instability in the model. Another interesting feature of GPT-3 that it actually can, and also of in-context learning, that the model can learn to use new words through explanation only, but this knowledge does not persist beyond the prompt time. So, for instance, we can prompt the model by explaining what word fardoodle means, and then the model will continue generating text that uses verb fardoodle in the correct context, and also manages to conjugate it properly. It understands that it's a verb. So here's another example of how GPT-3 can actually generate GSX comments just based on the text description of what user interface is required. And the opportunity here is that we can have a Nokish model for anything really through just a handful of demonstrations. And this is kind of relates to language-based programming. However, if we care about a particular task and want to achieve competitive performance, the fine-tuning is still something that we need to perform. Another problem with models of scale of GPT-3 is that because of the amount of data that they need to be trained and amount of compute that requires to train them. So for instance, the cost of compute for training GPT-3 model is in order of millions. So it's very costly to retrain them. And so this also means that the model essentially gets stuck in time because there is no other way to update knowledge in their weights without retraining. And then this leads us to our next topic, retrieval-based models. I just wanted to ask if there are any questions so far. Okay. Retrieval-based models. So as we just saw, training on massive amount of text enables the model to do in-context learning and remember factual information in its weights. But there is a limitation. So this information is compressed and we do not have easy control over what the model knows well and what it doesn't know. And language models are known to be prone to hallucinations. So hallucinations are the fluent text that is senseless, so makes no sense or factually incorrect. Consider this example. So we prompt GPT-3 with question, what did Albert Einstein say about dice? And then the model answers, he said, I never throw dice. And then we prompted with a couple of more questions. And each time GPT-3 provides answer, it never says that it doesn't know. It provides an answer. The answer sounds plausible. It sounds grammatically correct and fluent. But do you think any of these citations are genuine? Again, it's hard in webinar format. So the answer is no. So none of these citations actually belong to Einstein. And in fact, an example of model hallucinations. So yeah, so this the two main problems of large-scale language models, so the hallucinations and lack of factual grounding, and then the other one is keeping knowledge in the way it's up to date is computationally expensive. Can we instead allow the model to query a knowledge source and use retrieved evidence to make answer more accurate? So here we're looking at a model called Retrieval Augmented Generation, which was developed for question and answering task. So it starts with user asking a question, for instance, define middle ear, or fact verification query, Barack Obama was born in Hawaii. So the model does not try to answer this question straight away. Instead, it issues query to retriever. Retriever in this case is implemented using dual BERT. So questions and passages are embedded using BERT, and passages, for instance, Wikipedia articles. It's often quite usual source for question answering experiments. And then we use a dot product as a similarity measure to find passages that are more similar to the question. We collect top key passages, and then we go back to our language model. So we use retrieved passages to condition language model that generates an answer. For instance, we can condition by concatenating the question and passage text and passing them into prompt. So what does Retrieval augmented model does differently? So first, if we only use parametric knowledge, rely solely on a trained language model, then what model does during generation essentially tries to estimate the probability of answer given question. And this is conditioned on the parameters of the language model alone and information stored in the weights. So now if we, in addition to the language model generator, also have retrieved passages, we can estimate answer probability differently. So now we estimate answer probability, we factorize it essentially, taking into account probability of passages given question. This comes from our retrieval model, and the probability of answer given question and passage. And this comes from the language model generator. Does conditioning on evidence actually help? So does this complicated procedure with retrieval and more sophisticated conditioning works? So here's the example of result for natural questions dataset. So natural questions is the question answering dataset compiled from actual information seeking queries to Google. The x-axis in this case is the number of retrieved documents. And as you can see that, first of all, one observation is that the more documents the model is allowed to read, the better performance is, until it plateaus after about 30-40 passages. Another thing to mention, and something that is not shown on this chart, that without conditioning on evidence, accuracy of a fine-tuned model on this task is only 20%. So reading even a single passage improves performance from 20% to 39%. And so the accuracy here is measured as a string match between reference answer and generated answer. Another example from a different experiment. A dialogue, enhancing a dialogue agent with retrieval. A user asks, Thierry Henry is one of my favorite players. What about you? And then gold answer annotated by human annotators. He was good. He is a retired French professional footballer. So parametric model without access to external knowledge provides an answer, but the answer is completely off from factual perspective. And then at the bottom, there are examples of answers generated by a retrieval augmented model. So the model gets correctly that he is a French professional football coach and a former player. Recently, DeepMind also published a paper on using retrieval for language modeling. And here, researchers scale knowledge corpus even further. So instead of using Wikipedia, they look at massive text, which is a DeepMind proprietary data set that consists of about 2 billion documents. The challenges of this work and of the retrieval augmented generation in general, particularly for language modeling, are twofold. One is how do we go about evaluating the results? Once our data store becomes so big that it contains potentially contains large chunks of test set, we have to be very careful when interpreting our results. And then the second challenge, how do we pre-train supervised retrieval at such scale? So for instance, for retrieval augmented generation work that I discussed on the previous slide, retrieval, we retrieve from Wikipedia, which is 9 million passages, 9 million documents, and we pre-train neural retriever in a supervised way. However, to scale this to 2 billion documents is a substantial engineering challenge. Yes, so as we see, retrieval augmented models are great, but where is the catch? Accuracy of retrieval and ability of language model to recognize which passages are the most relevant is crucial for good performance. However, it is still a challenge to find to achieve good recall, even for relatively simple questions. For more complex and abstractive questions, retrieving relevant articles is hard. Depending on the type of retrieval augmented model, we might need to sample at scale. We might need to sample many candidate answers and then use model to score their probabilities, and all this process effectively increases the requirements for inference time compute. And finally, maintaining and keeping up to date large knowledge corpus and retrieving from this corpus creates substantial operational overhead and increases memory requirements. So what if instead of maintaining our own retrieval corpus and dealing with all technical challenges, we outsource this function to commercially available search engines? Put things in perspective, put numbers in perspective. So as I mentioned, Wikipedia contains about 9 million documents. DeepMind massive text contains 2 billion documents. And according to this article that was published in 2016, Google Search knows about over 130 trillion pages. So potentially, we can expand information available to our models by several orders of magnitude. And in fact, this is something that caught attention of many research groups across the world. And here I will be talking about how Google Search is used in Google LaMDA model that has been recently released. So we start with a user statement or the user question: when was the Eiffel Tower built? And then there's several flavors of LaMDA. So there's LaMDA base, which does not have access to any external knowledge, and essentially, as a parametric model generates a draft response. And then at the next step, another flavor of LaMDA research, which is trained to generate queries to toolset. Toolset in this case consists of Google Search Calculator and Translator. And then it extracts the information from Google Search. This information is then again propagated through LaMDA research model, and LaMDA research model is fine-tuned to decide whether the information is sufficient to provide an answer to user, or further information is needed. And if further information is needed, LaMDA research reformulates query and collects more information. And finally, after several iterations, LaMDA research decides to generate output to the user once the information collected is sufficient. So what happens is that it verifies the initial claim generated by LaMDA base, and replaces the unverified part with a different statement based on the source found using Google search. This is accuracy and ethical considerations at evaluation time. So LaMDA is fine-tuned not only with task-related generative objectives, as we usually fine-tune for downstream applications, but also it uses discriminative objectives that evaluate safety and quality of a response in context. And these discriminative objectives, their aim is to bias the model towards safer, more interesting and grounded replies. So, for instance, the metrics that are used in this discriminative function are sensibleness, safety, specificity, groundedness, interestingness, informativeness. And we compare the LaMDA-based pre-trained model versus LaMDA fine-tuned in pink, and we see that LaMDA fine-tuned with these objectives performs better than simply pre-trained LaMDA-based. In some cases, it actually reaches human level and outperforms, particularly in case of for the informativeness. So the human annotators who didn't have access to information retrieval system during annotations, baseline for informativeness of the answers is actually lower than what LaMDA manages to achieve. So the internet augmented models is rapidly expanding area. So it started last July with BlenderBot 2.0 paper, and then there was the WebGPT published by OpenAI in December 2021, and Google LaMDA released the paper in January. Takeaway messages from this part. Scaling up transformer architecture led to breakthrough improvements in NLP and enabled few-shot learning. We do not need massive amount of data for each new task. The current trend of extending language models with retrieval, either using offline neural retrieval or using Google search, further improves factual accuracy and groundedness. At the same time, we see that scale alone is not equally useful for all tasks. Tasks that require complex reasoning or common sense, something that is usually so obvious that people tend not to say or write it, still require bespoke solutions. And on this, I'll pass to Angeliki to talk about ethical considerations, unless you have questions.
Elena, can you keep presenting maybe? Well, I mean, as Elena brings up the slide, so there is this saying that says, with great power comes great responsibility. And I mean, it's definitely true, as like Elena has talked about like all the recent breakthroughs. So these models are really, they have a lot of power. I mean, we still, like from the research perspective, we still have a lot of things to do to really unlock and improve on a number of directions. But even as they are today, they can do some amazing things. So they have a lot of power, and we need basically to treat them in a responsible way. And that on its own, it's I guess is not a problem. What is tricky is that it's not so easy to navigate this space, especially because these models, as Elena mentioned before, they are trained on unprecedented amounts of uncurated data. And seeing what a model learns from a bunch of random text on the web and predicting what happens after 96 layers, each with 96 attention heads, it can be quite unpredictable. So this is overall a pretty tricky business. And as you can imagine, because of the complexity, there is a multidimensional, ethical and social risks. I think it would be interesting, at your own time, we will put the slides there to look at those, ethical considerations and, ponder a bit. We have, some expected things like, for example, discrimination, exclusion, and toxicity, which can arise. For example, I guess, you've all seen Reddit, and, you see what happens in Reddit, not every particular subreddit, let's say, is sanitized and let's say nice. People say all sorts of things, and when we train our models there, it's inevitable, that some toxic language might come out. We have, for example, cases of even, commercial systems today latching on particular biases, which that they don't even need to be toxic per se, but, there are biases that can cause harm. For example, we have machine translation systems that still till today occasionally associate doctors with he, with a pronoun he, and nurses with pronoun she, completely out of context. And this is particular, for example, when you go from languages like English to languages like Greek or Romanian, because these languages have we inflect adjectives basically based on the pronoun, whereas in English we don't do that. In Twitter, you've probably, you've seen all the amazing things that Copilot could do, and really amazing things, but there is the flip side of that training, scraping GitHub and training on it had also some unpredicted consequence of, occasionally leaking private information. Elena already talked about using internet with our models. Again, internet is anybody can post anything on the internet, and it's a key consideration when you use the internet augmented models to make sure to not be disseminating basically wrong information from the internet back to the model, back to the user. Can you go to the next slide, Elena? Thank you. Of course, with any application, there are the good usages, but there are also the bad usages that arise from, actors, for example, using language models to intentionally cause harm. Now you would think, how can an actor, or how can I cause harm, with a language model? But as Elena showed, because even in this poetry, was it Shakespeare poetry or something? The text was nice and fluent, and imagine if you are a bad actor, we can basically generate in mass fake news and start spreading them everywhere, and a lot of other things basically. But yeah, these are not things that they should stop us from developing big models, but we should be doing this in a sort of ethical way, and be considering the ups and downs and all the ways that this can be used in a way that we, the developers of those tools, were not intended for these tools to be used, so that to arrive at some point at a situation where we can have basically these models not being used in ways that they create harm, for example, to their users. And I'll leave it at that.
Thanks, Angeliki. Are there any questions so far? Otherwise, we still have, I think, a couple of slides to discuss. I will very briefly highlight one very exciting work that recently was done in DeepMind. And it also relates to this problem of scale not necessarily being sufficient for improving performance on some more complex reasoning tasks. So I will be talking about AlphaCode. So AlphaCode is the aim of the project is to create a model that could participate in competitive programming. It currently achieves roughly average human performance, I think, on the Codeforces competition. So how this model has been like what are the ingredients of this model? So the model starts with pre-training data. So the model is a pre-trained transformer-like model is pre-trained from scratch using GitHub data. And then it's further fine-tuned using a small subset of competitive programming examples. So on input of the model, we have problems, and on the output, solutions. And during fine-tuning, the model tries to map to generate, given the problem, generate solutions, and then use cross-entropy loss to the goal solutions. So as I said, yeah, pre-train on selected public GitHub code. At evaluation time, what is interesting here, at evaluation time, a model generates massive amount of C++ and Python programs for each problem. So effectively, it generates about a few million candidates for each problem. And then there's important step of filtering these candidates and clustering them so that to come up with a small set of 10 candidate programs that then can be submitted to for external assessment. So because of only 10 submissions are allowed, and so from this 1 million candidates, we need to then distill and find 10 most promising solutions. So this chart shows how development of the model went. So what a kind of key turning point, what decisions affected performance of the model and how. So the y-axis here is the performance, and then we have this average human competitor in magenta, and then top human competitors in cyan. So we're not there yet, but we're roughly reaching the average human performance. So I wanted to highlight two modifications to the model. The usually large-scale language models, like very large-scale GPT-3 or Gopher, which was released by DeepMind earlier in 2021, and they're decoder-only models. But here, the authors of AlphaCode project found that encoder-decoder architectures work better because they allow essentially bidirectional description representations. So when the model looks at the problem definition, the tokens at the beginning of the description can attend to the tokens at the end, and vice versa. And so this ability to build a holistic representation, essentially, of the problem definition is helpful. And then another another improvement is this clustering. So as I said on the previous slide, filtering and clustering essentially allows us to go from 1 million candidate answers to 10 best candidates that we then can submit for scoring. And clustering is an important step here because in itself, the model tends to generate candidates, many of which are similar. And so clustering helps us basically to find solutions which are similar. And when we then select the top 10 candidates, we only sample once from each cluster. And then finally, the scaling up part comes towards the end. So scaling up, after all this additional modifications were introduced, scaling up helps the model to improve performance by another 4%. But now, as you can see, the starting point was about, I think, 4% here. And so between 4% and 30%, these are the kind of smart task biases that help to drive performance. And this basically suggests that as much as we enjoy scaling up transformer architecture, we still need to consider other tasks and think about task-specific solutions, particularly in areas where we see that scaling does not bring the let's say proportional improvements in performance. I think that is all from our side today.
Okay, so sorry for interruption. If anybody have question, please raise your hand and write it in chat or interact with us in any form. Okay, sorry. Okay, you didn't want to say anything else?
I have a question actually that I mean I would like to ask people or people in this call, which is what people think. I mean, what is the type of application people would be excited to see with these models? So something that the people will feel excited to see this happening at some point. I don't know if anybody wants to answer here, either people watching the tutorial or people like Miruna or Elena.
Tutorial will be very fun.
Sorry, what?
I think.
Yeah.
Oh, okay, you can hear me clear. Okay, so I think a tutorial would be very fun if you'd like to, I don't know, to hold one sometimes. A tutorial with an application, with any application that that actually implement one of the things you presented today. Because we can see the theoretical part, but there are some college students or high school students that understand the concept, understand the abstractization of the concept, but don't know how to implement that. Like, in fact, don't know. So I think there are some people here that would like a demo or something implemented. So if you have time and like to present a demo, not today. I don't know. In another day that we can talk about.
I think there on the topic of like understanding better how these things work and how they're implemented. There are a number of excellent collabs available that actually look at how fine-tuning of transformers is done, for instance, for downstream tasks, for question answering. So if there is interest, we could we could point the interested people to those collabs. But yeah, they're also publicly available.
Okay, so would it be easier, or I don't know, okay for you to leave us in the last slide some useful links, some contacts that participant can ask you? I don't know, some emails, or that will be public. I mean, these will appear on our website, so you have to consider that when you put information there.
I mean, we can.
Would it
So we will definitely add some information on the last slides for people to, in their own time, to process as they see fit.
No one will venture with ideas for amazing applications and tasks.
Okay, that would be great. Oh, wait, I can read that my colleague is trying to say something, but we can't hear.
No, we can't hear anyone.
It's okay. Lucian, if you want to say something, write in chat. Okay, he said something about biology application of that technology that you presented and AI concept in general. So that was the idea that he wanted to share with us.
Yeah, I mean, there is like like this is an amazing opportunity to start, at least prototyping things in different domains and for different tasks. So it's, I mean, if people have time and, they have appetite, it's something that we could, we like, I was discussing with my partner that, now is the right time to be doing these things. There are like so many tools available, like, compared to what there was there 5 years ago, where, we had to implement things in MATLAB, like neural networks. Now, it's in some way democratized. So we are going to put some links on the slides for people, to try models out and see for themselves, what models can do, and some other things that, models cannot do yet, with the hope that, people can get inspired, and like, as they get more acquainted with this technology, can themselves like have a way, to innovate either algorithmically or technically. So yeah, it's an exciting time for you people to be learning and working on these things. Yeah.
Okay, so it seems like they had a good start by now with the technology, and yeah, it would be very, very useful to have some links that they can look over after the live presentation.
Sounds good.
Okay, so there are other questions, some from attendees, some from colleagues. Anything else?
Where do you see questions? I don't see any questions.
Or do I? I just wanted to make sure I didn't, I don't know, ignored one by mistake. Okay, so thank you so much for coming and presenting such interesting information. We hope to collaborate and learn more from you, because we have a lot to learn from you in the future. So yeah, you please let some contacts in the last slide, and thanks again for the presentation.